in words, I mean, this is a conditional expectation. So it says that if you're outside of this small set, you have this geometric contraction. Actually, that's the way you should think about it. I mean, by the Markov property, taking the conditional expectation given xt is the same as taking the conditional expectation by the entire past. And so it says that if I want to look at the conditional mean of this cost function or value function or whatever it is, one step in the future, lambda is less than 1, I get this geometric contraction. Whenever I'm outside of this set, which is always going to be compact, bounded, any application you look at, S is going to turn out to be a bounded set. Any physical application, right? That's what you find in practice. The theory doesn't require that, but that's what you see in applications. So that's a reasonable way of thinking about stability, because V is going to blow up too in typical applications. If X is large, V will be large. And it says if I'm far away from the center of the state space, I come back down with a geometric contraction. So it's not surprising that it implies some form of stability, and it gives you just the kind that you would hope for, the sort of geometric ergodicity. Okay, so remember that so we have okay. I guess I need aperiodicity as well. We've got assume that. And then we get the generalization I said last time. Before I talked about this for countable state spaces, so I'm able to say probably from X to Y, but now we would say probably going from X to a set converges to the steady state distribution at a geometric rate. Okay. So tell me what the Lyapunov function will be. Definitely not this linear thing. We just saw that only goes down at rate 1. So how would you get something that what? Yeah, no, that didn't work last time. So if you go back to like a week ago, a quadratic failed. So quadratic, if you have v of x equals x squared, we saw a while back that we get that v3 condition. This f is going to be like linear. But I've said it has to be bigger or equal to 1, so f is going to be equal to 1 plus epsilon x. So you can, so we lose a moment. If you put x to the 5th here, you get a 4th here. Yeah. What's that?
Or better Lyapunov function.
Nah. No, doesn't matter. No, I don't need to scale it. Anyway, this is what I get. For some epsilon, I get this for f. Right? So it's not a polynomial. That's the thing, is that it has to be unnatural, because it's not like a linear system. Linear systems like that you're used to for a control course, they naturally have a geometric contraction. But this thing has this awful, boring, slow, drift downwards. So in order to have a geometric drift, you have to do something weird with the space.
Use a trace.
Trace. There's no matrix here. Now I'm looking for a function. So we found to get Fars's criterion, we get a linear function, and we get this negative drift. And if we get a quadratic, we get a linear drift. And if you go back to the notes from a week ago, you'll see that. So what would give a geometric drift? Well, remember, the bigger we get, the bigger the drift. So if let's change this. If I put an 8 there, I'd get a 7 there. So I need a big function, not a small function. A log will give me a drift of 1 over x. Minus 1 over x. That's not going to help us. Yay! E to the x. Now, e to the x might not work. The reason it might not work is dv might be infinite, So you got to put in a little epsilon there, and that's going to work. And this is useful to go through because we get to practice our log moment generating functions, although we're almost out of time, are we? What time is it then again?
7.
What?
7 minutes.
We have 7 minutes? All right. So play the same game as before. If you look at PV of x, all right, so I'm just plugging in what xt plus 1 is. It's just yeah. So given I'm at x, I just add on an increment, and I take the max with 0, and that's it. And what I can do is I can actually multiply. I can multiply it times e to the minus epsilon x and e to the epsilon x as this 1. And I can do that to put these two together to get the same thing I had before. The product of the exponentials is the exponential of the sum. And so by doing this, I can subtract the x there and subtract an x there and get something very similar to the way I had before. So this is v of x, right? And this I'm going to, take the product of the exponentials, I get the sum inside. All right. It's hard to read. Okay, once more. I had this from the definitions, and I did is I multiplied and divide by v of x. And that division by v of x, I can go through and yes, and I knock out the x there and I move it there. So I just brought that inside the expectation. Just a bunch of algebra. I'm not going to go, All right. And that looks like a moment generating function. So we can actually use our delta x intuition here to get a bound on this monster here. Let's just do that. So let me define lambda of epsilon x to be the log of that puppy. All right. And this is a nice convex function of epsilon. Remember all that? This is just for fixed x, as a function of epsilon, this is our convex function that we know and love. So epsilon is a variable, x is fixed, and it's infinity sometimes. And we know it hits 0 and becomes infinity again, because it's not finite everywhere possibly. And does anybody remember what the slope is? It's a log moment generating function. You said it right. The mean. And what's the mean of this guy inside? It's my minus delta of x. So the mean is exactly minus that. All right. So okay, that's what's important. The fact that the slope is negative for, say, x greater equal x bar. This is delta of x, not minus delta of x. And so if the log is negative, then the thing inside is less than 1. So basically what I could do is I can say, my conclusion is that PV of x is less than or equal to some lambda of x times v of x just give it a name, call it lambda of x. And that's going to be, say, less than or equal to the exponential of minus epsilon delta over 2. So with another half an hour, I could give you the Taylor series approximation exactly. But by doing this, you can get a fixed epsilon. So this is true. All x equal x bar, the same x bar as before. Just taking exponentials of both sides. All right. So there it is. So you get conclusion. It's geometric ergodic. If and only if what? What assumption did I make? I need a moment generating function for delta.
I think it must be clustered and can't spread it out.
Okay, so you need this moment generating function to be finite in some interval around 0. And obviously, if delta 1 is bounded, there's no problem. It's finite for all epsilon. So that's a typical case. All right, so random walks are geometrically ergodic. You now know that. And you have an almost complete proof. So that concludes. I think we're out of time. In terms of next steps, we're still working on it. I want to get out of the theory and into the algorithms as much as you all do. And we will have a plan in the next 48 hours and send it to you. There'll be a bit of more Markov stuff next week and then on to statistics. All right? Okay. And have a good weekend.